Hello and welcome to Sleepy Story. Tonight, let us drift into a corner of the universe where light speaks in whispers and whole cities of stars pass almost unnoticed. We are going in search of the galaxies that hide at the threshold of vision, dim, delicate, and so thinly spread across space that a careless glance might miss them entirely. Before we set off, I would love to know where you are listening from. Maybe you are tucked beneath a blanket with the room lights low, or sitting beside a window with a calm night outside. Or perhaps you are somewhere bright and busy, using these words to build a small island of focus. Wherever you are, thank you for keeping me company beneath the same sky. If these late-night journeys bring you a sense of calm or wonder, please consider subscribing. Every new subscriber is a spark of encouragement, a gentle push that helps me keep making stories like this. Quiet explorations for curious minds who enjoy learning at a peaceful pace, and a small warning. I will try to keep things soothing, but the mystery we are about to explore can be gripping. If you stay awake longer than planned, at least you will carry a new idea into sleep, like a lantern kept glowing behind closed eyes. Imagine a telescope trained on what first appears to be a blank patch of sky. The detector collects photons with patient discipline. Minute by minute, the blackness softens and faint smudges rise into view. Not dust on the sensor, not tricks of the eye, but vast structures floating in the deep. A few are familiar, spirals with bright cores and arms sprinkled with newborn stars. Many others feel different. Their light is spread so thin that even long exposures barely gather enough to outline them. Astronomers catalogue some of these as ultra-diffuse galaxies, systems so extended and faint that their stars seem like embers scattered by a distant breeze. Where do such fragile giants come from? A galaxy is usually a balance between gravity that pulls material inward and pressure from stellar birth, supernova winds, and black hole activity that pushes gas outward. In the grand cities of the cosmos, those forces carve elegant shapes, disks, bars, bulges, halos. But in these silent realms, everything appears subdued. Gas arrives slowly. Star formation proceeds in fits and starts, then falters. The result is a structure that covers a large area but holds very little light, like a sketch traced in chalk and thinned by the rain. Some of these galaxies live in clusters, where tides and encounters can stretch and dilute them. Others float in relative isolation, adrift in the dark between the brighter metropolises of stars. A few even challenge our assumptions about what holds galaxies together. Most galaxies sit inside halos of dark matter, the unseen mass that provides the deep wells in which gas can collect. Ultra-diffuse systems sometimes appear to have halos that are unusually light for their size. Others display motions that imply very massive halos despite their faintness. Each new measurement pushes theory to adjust, to consider histories shaped by stripping, stirring, or unusual birth conditions. To understand their hush, we return to first principles. Surface brightness, the light per unit area, fades quickly as a galaxy spreads out. Even if two galaxies contain the same number of stars, the one that stretches those stars over a larger canvas will be far harder to detect. On top of that, expanding space dims distant objects through the Tolman effect, a gentle but relentless drop in surface brightness with distance that punishes faint, extended structures most of all. Telescopes fight this unfair contest with time and technique. Long exposures, careful subtraction of sky glow, and lenses designed to reduce scattered light that would otherwise paint a false veil across the scene. Consider an instrument built with that purpose in mind. Arrays of fast telephoto lenses that minimize internal reflections and chase low surface brightness features spread across large fields. Add wide surveys on the ground and in space, and suddenly the blank patches of yesterday are strewn with ghosts. Streams torn from galaxies by tidal forces, halos that were previously invisible, and whole galaxies that seem barely to cohere. The more we look for faint structure, the more the universe reveals that it has been writing in pencil as well as ink. These galaxies also carry clues to the history of rionization, the era when the first stars and black holes bathed the cosmos in radiation strong enough to strip electrons from hydrogen gas. Small halos may have struggled to keep their gas during that turbulent dawn. A single burst of star formation could consume or expel what little fuel remained, leaving behind a pallid system that drifts through time with only a few aging stars to mark its existence. In denser environments, ram pressure from hot cluster gas and the gravity of giant neighbors can peel away material, turning normal systems into wisps that still count as galaxies, but resemble tide lines after a receding storm. Not all silence is weakness. Some dim systems hold surprising mass in dark halos, suggesting that stability can exist even with very little starlight. Their orbits, traced by the Doppler shifts of red giant stars or by delicate globular clusters, can reveal deep potential wells that the eye cannot see. Others seem almost weightless by comparison, perhaps because tidal forces have rearranged their contents, or because past interactions robbed them of the usual anchors. When we chart these objects, we are forced to accept that our census of galaxies has been biased toward the loud and the bright. The universe has a quiet majority. If ultra-diffuse systems are common, they may contribute significantly to the overall inventory of stars and to the tracers we use for dark matter. They may also explain puzzling streams and shells around larger galaxies, fossil signatures of past meals on a long-finished menu. There is a human side to this search. Observers plan nights around the darkest skies, careful calibration frames, and fields chosen to avoid scattered moonlight. Data pipelines must treat the sky not as a flat background, but as a living, changing light. Even a trace of reflected glow from the telescope structure can masquerade as a faint halo. Teams compare methods, swap techniques, and test each other's claims with the skepticism that good craft demands. When a new ultra-diffuse candidate is announced, the community asks for confirmation. Deeper images, velocity dispersions, star counts that confirm membership in a cluster instead of masquerade as a foreground smear. The silence of these galaxies is more than an observational hurdle. It is a philosophical invitation. Brilliance draws attention, but absence can be eloquent. A dim disk whose stars are scattered thinly across 100,000 light-years says something about cosmic nurture and neglect, about the balance between creation and erosion. It reminds us that not all success in the universe looks like fireworks. Sometimes survival takes the form of endurance without display. Stand with me in the mind's eye, on a gentle ridge under a dark sky. The Milky Way arches like frost across black glass. Somewhere inside that band, and far beyond it, the silent ones drift. Their light arrives as a trickle, patient and polite. No trumpet announces them, but if you give them time, they step forward from the gloom, a hairline curve here, a diffuse oval there, the barest signal that a deep structure holds. There is comfort in this patience. The universe does not force disclosure, it rewards attention. Each quiet galaxy is a reminder that discovery is built from ordinary discipline. Exposures stacked night after night, calibrations repeated, assumptions questioned, and small improvements gathered until a threshold is crossed and the hidden becomes visible. The map of the cosmos is not drawn only by spectacular bursts, but by soft accumulations of care. In the episodes ahead, we will ask how these systems form, why some seem to lack normal companions, and what their demographics tell us about the scaffolding of dark matter. We will look at the tools that make them visible and the traps that have fooled us before. We will also follow a few case studies whose stories bend expectation. A galaxy whose motions imply a massive halo with barely any stars, and another whose motions imply a starry puff with almost no halo at all. Each one is a reminder that nature writes exceptions into every rule. For now, breathe slowly. Let the thought settle that, across extraordinary distances, there are galaxies the color of ash, as broad as our own, holding themselves together with only a hint of starlight. They are not loud, not proud, not made for postcards. They are the quiet rooms of the universe. And because they exist, our portrait of creation becomes more honest, less theatrical, more complete. If this calm journey has kept you company, you are welcome to return for the next chapter. Your presence makes these nights brighter than any screen. Thank you for listening, and thank you for caring about the dimmest things that still glow. When astronomers speak about the faintest structures in the sky, they are really speaking about the art of subtraction. A dark image is never truly dark. The night has a glow of its own. The atmosphere breathes. The optics of a telescope scatter tiny halos around stars. Detectors add their whisper of electronic noise. The Milky Way contributes a diffuse sheen of starlight. Even the zodiacal light lays a thin film across the frame. To reveal the quiet galaxies hiding inside this luminous fog, observers must remove layer after layer without erasing the very thing they hope to keep. It is a discipline closer to restoration than conquest, a careful lifting of varnish until the painting underneath can breathe. Surface brightness is the critical measure. A bright galaxy can be distant and still obvious because its light is concentrated. A diffuse galaxy can be nearby and remain elusive because its light is spread thin. The threshold between visible and lost is not a sharp line but a slope, and the slope is steep. Double the radius over which light is spread, and the surface brightness falls by a factor of 4. Then distance dims it again. The farther we look, the more the cosmic expansion reduces surface brightness through a quiet mathematical penalty. These principles are impartial. They obscure everything without fear or favor. The silent galaxies simply live most of their lives on the far side of that threshold. To approach them, observers design instruments that treat scattered light as the true adversary. Coatings on lenses are refined to reduce reflections. Baffles and dew shields extend like careful sleeves around optics. Arrays of fast telephoto lenses point in unison so that their images can be combined, gaining depth without inviting the scattering that large mirrors sometimes produce. The strategy is straightforward. Avoid making false halos. Then spend the saved effort collecting the very faint halos the universe already drew. The method can feel old-fashioned, like a choir of small voices outperforming a single great soloist by teamwork and balance. But hardware alone cannot deliver the quiet. Data must pass through a river of calibrations. Flat fields correct for sensitivity changes across the detector. Bias frames capture the fingerprint of readout electronics. Dark frames reveal thermal noise. Then comes sky modeling, building a picture of the background that can be removed without carving out the galaxy itself. Algorithms learn the shape of the sky from empty regions of each frame. Mosaics stitch together overlapping exposures so that what is real lines up and what is spurious cancels. The reward for this patience is a view in which dim arcs around massive galaxies become visible. Streams of torn stars trace ancient encounters, and whole ultra-diffuse systems announce their presence as pale ovals, holding just enough starlight to insist that gravity has done work there. The stars inside these dim beacons are usually old and metal poor. Their colors, measured with long exposures through different filters, lean toward the subtle tones of aging populations. Red giants with slow heartbeats, subgiants crossing quiet thresholds of evolution, main sequence stars too faint to register except in composite. Blue patches sometimes appear, signatures of a belated breath of star formation after the system drifted through a cloud of gas, or perhaps echoes of an encounter with a passing neighbor. But the palette tends toward understatement, and the story it suggests is one of restrained growth. Fuel came in sips instead of streams. How then do we learn masses from such whispering systems? Individual stars are difficult to track because they are faint, and integrated light is perilous because it is so easily contaminated by the sky. One answer lies in globular clusters, dense knots of ancient stars that orbit like bees around a hive. Even a faint galaxy can host a surprisingly rich population of globulars. They are bright enough to stand out and compact enough to measure accurately. By counting them, by mapping their positions, and by measuring their Doppler shifts, astronomers infer the gravity field of the host. A generous swarm suggests a deep halo. A sparse population hints at a light one. In some dim galaxies, the clusters appear almost extravagant, as if the system invested its meager starlight disproportionately into these luminous knots. Velocity dispersions provide a second line of evidence. Spectrographs gather the faint glow of many stars at once and analyze the spread of their speeds along our line of sight. Even a handful of good measurements repeated carefully can anchor an estimate of the total mass. The surprise is how varied the results can be. Some ultra-diffuse galaxies carry motions that imply massive halos, solid and deep, with starlight only a delicate frosting over hidden weight. Others appear almost weightless by comparison, as though their halos were stripped away in past encounters or never grew as expected. These extremes resist easy classification. They speak of diverse histories instead of a single template. Distance is a third challenge. A smudge may be near and small, or far and grand. To know which, astronomers reach for surface brightness fluctuations, a method that uses the graininess of unresolved stars. In a closer galaxy, the random scatter of bright red giants from one patch to another is larger. In a distant one, the light blends more smoothly. The strength of that statistical grain becomes a yardstick. Another path uses the tip of the red giant branch. At known distances, the brightest red giants hit a predictable ceiling in luminosity. By isolating those stars with deep imaging, observers can step a galaxy onto the cosmic ladder with a precision that transforms a mystery into a measured member of a group or filament. The environment offers an additional set of clues. In the outskirts of clusters, dim galaxies often trail streams, as if a slow tide were peeling them into the intracluster medium. Ram pressure from hot gas can strip them of the last reserves of fuel, locking in their quiet. Near massive ellipticals, pale companions show signs of tidal stirring, their shapes elongated along orbits that hint at long relationships of dominance and surrender. In the field, far from clusters, some ultra-diffuse systems float with surprising serenity, their meager stars arranged in smooth disks or spheroids, untroubled by the storms that rage in denser quarters. Whenever one of these galaxies breaks the mold, the community leans closer. A system whose motions match the stars alone, with little room for a dark halo, triggers debates about measurement and modeling. Another whose motions require a deep halo, despite almost no starlight force's reflection on how galaxies collect and keep their mass. Skepticism becomes a virtue here. New observations check old ones. Independent teams revisit the same field with different instruments, compare reduction pipelines, and publish not only results, but methods so that uncertainties are visible and progress is honest. Silence in astronomy is rarely empty. It often hides a syllabus. The ultra-faint narrate chapters on feedback, how supernovae and stellar winds push gas outward and set the pace of future birth. They teach about quenching, the ways galaxies stop forming stars, whether through environmental processes or internal exhaustion. They instruct on thresholds, minimum halo masses required to gather and retain fuel, minimum metallicities to cool efficiently, minimum surface densities to trigger collapse. What they do not do is shout. They allow themselves to be understood only by those willing to look long. For observers on the ground, conditions are as much a part of the experiment as the telescope. Moonlight raises the floor, humidity scatters it, airglow lines wander, cirrus lays a translucent curtain that no amount of later work can fully remove. Nights in which everything aligns, dry air, steady seeing, calm winds, mechanical stability, are treasured like rare coins. Planning becomes an act of astronomy in its own right. Choose fields at high galactic latitude to avoid the wandering dust of our own galaxy. Select roll angles to keep bright stars from placing their halos where the galaxy lies. Build dithering patterns that move the sky across the detector so that defects reveal themselves and can be corrected. In space, the game changes, but the theme persists. Instruments free of atmospheric turbulence can stare longer, with more predictable backgrounds. But even deep space telescopes face stray light from the Sun and Earth, thermal drifts that alter sensitivity, and subtle reflections within complex optical trains. Teams learn the personalities of their instruments and fold those eccentricities into their calibrations. The reward is imaging that reaches surface brightness levels unattainable from the ground, where diffuse halos around galaxies come into view like fingerprints in oblique light. There is a special joy in stacking. Many exposures of the same field, some short, some long, some taken at slightly different pointings, are aligned and combined. Random noise cancels. Constant light accumulates. Features that were merely possible after 1 hour become confident after 3, persuasive after 10, and quietly undeniable after 20. The brightness of the sky does not surrender, but its variability does, and the galaxy emerges. For students learning the craft, this moment feels like a curtain pulled aside. The image before and after stacking almost appears to be a different universe. The stories of individual systems, once isolated curiosities, now join a chorus. Catalogues grow, demographics emerge. Faint dwarfs appear more often around certain hosts than others. Ultra-diffuse disks show hints of rotation in some environments, and only random motion in others. Metallicities trace families of origin. Globular cluster counts correlate with halo mass in ways that refine how we assign mass to light when light is scarce. With every accumulation, models of structure formation adjust, learning where galaxies grow slowly and where they are pruned into wisps. All of this is technical, but the feeling it leaves is simple. The universe contains quiet rooms, and we have learned how to open the doors without turning on bright lamps that would change what we came to see. The silent galaxies beyond reach are not miles outside our curiosity. They are only inches beyond our habits. Give the night more time. Sharpen the care with which you prepare the tools. Ask less of brightness and more of patience. When that shift takes hold, whole neighborhoods appear where nothing seemed to live. Before we move on, hold one image in mind. A broad, pale oval suspended against a field of tiny stars. No bar, no spiral, no glare. Only a suggestion of structure and the knowledge that it endures. That gentle presence is not the absence of a story. It is a long story told softly. In the next chapter, we will follow its likely beginnings, how small halos learned to gather fuel in a freshly ionized cosmos, how feedback sculpted their destinies, and how tides wrote marginalia around the margins of their pages. When you trace the story of a galaxy back to its origins, you find a web of chance, environment, and timing. Some galaxies flourish, bright and intricate, weaving spiral arms or collecting gas for millennia of steady star formation. Others grow quietly, thin and fragile, their light spread across improbable scales. These silent galaxies, so faint that whole catalogues overlooked them for decades, did not arrive at their condition by a single path. Instead, they are outcomes of many histories, written softly in gravity and time. One pathway begins in the earliest epochs, not long after reionization swept across the universe. The first generations of stars lit the cosmos with fierce ultraviolet radiation. That light heated intergalactic gas and made it difficult for small halos to gather new fuel. Some halos, just massive enough to collect gas before reionization, formed a handful of stars and then stalled. They became fossils, still drifting today as faint dwarfs or diffuse systems. Their silence is ancient silence, the hush of interrupted growth. Another pathway is more dramatic: tidal encounters. When a smaller galaxy passes near a larger one, or through the dense core of a cluster, gravitational forces stretch it. If the orbit repeats over billions of years, stars are pulled outward into streams, and the main body puffs up. In this way, a galaxy can grow large in size without gathering more mass, its light diluted across a broad canvas. Some ultra-diffuse galaxies discovered in clusters bear scars of this history. Elongated shapes, disrupted star distributions, faint arcs stretching away like ghostly trails. A third path involves internal feedback. Stars are not gentle tenants. When they explode as supernovae, they push gas outward with fierce winds. If a galaxy is small, the blast can expel much of its gas entirely. Without fuel, star formation fades, leaving behind a skeletal structure. Some models suggest that entire populations of diffuse galaxies are the result of such over-energetic feedback, where the violence of early stars created silence for all the ones that might have followed. Not all silent galaxies are weaklings, however. A handful have stunned astronomers by showing evidence of massive halos of dark matter. One famous case, Dragonfly 44 in the Coma cluster, appeared at first to be nothing more than a smear of starlight. But when astronomers counted its globular clusters and measured the velocity of its stars, they found a mass comparable to the Milky Way, yet with only a tiny fraction of its stars. Dragonfly 44 is not an underdog. It is a hidden giant cloaked in faintness. Its silence comes not from fragility, but from invisibility. The counterpoint to this is even stranger: galaxies discovered with almost no dark matter at all. Systems like NGC 1052 DF2 and DF4 challenged expectations by showing that their stars moved more slowly than predicted. Without dark matter's hidden weight, how did they remain bound? Some scientists suggested they were tidal fragments, carved from larger galaxies. Others argued for errors in distance or measurement. Observations refined those debates but did not resolve them completely. The lesson was clear. Silence is not one story, but many. Consider also the role of environment. In galaxy clusters, the hot intracluster medium acts like a slow wind against anything that passes through. Galaxies that dive in may lose their gas through ram pressure stripping, leaving only faint shells of old stars. In groups, gravitational harassment can shuffle orbits and puff up systems into diffuse forms. In isolation, a galaxy might evolve with serenity, its diffuse shape preserved simply because nothing disturbed it. Each silent system is a case study in context. If you picture the cosmic web as a stage, then bright spirals and giant ellipticals are the actors who claim the spotlight. Silent galaxies are the stagehands, present everywhere, holding the structure together, but noticed only when you pause to look carefully. They remind us that astronomy, like life, is not built only from the dramatic, but also from the quiet. The variety of their formation stories makes them invaluable to cosmology. By counting them, measuring their masses, and tracing their environments, astronomers can test how dark matter behaves. If ultra-diffuse galaxies are common in clusters, it implies certain properties of halos and feedback. If isolated examples exist in abundance, it changes expectations about early star formation and the effects of reionization. Each faint oval on the sky becomes a data point in a larger pattern, part of a grand puzzle about how the universe organizes itself. Case studies sharpen these ideas. Dragonfly 44 whispers about massive halos wrapped in faint light. DF2 and DF4 murmur about a possible class of galaxies stripped of their dark scaffolding. Others, tucked into the Virgo cluster or orbiting Andromeda, suggest a spectrum of outcomes rather than a single archetype. Every new discovery adds to the chorus, making the silence paradoxically louder. The search for these systems has also transformed our technology. Dedicated arrays like the Dragonfly telephoto array, built from commercial lenses arranged to minimize scattered light, have turned the overlooked into the observable. The James Webb Space Telescope now adds depth by resolving individual stars in faint systems, confirming distances and memberships. Future surveys with Vera Rubin will likely expand the census dramatically, forcing theory to catch up with observation. The map grows richer with every year. It is worth pausing on the human element. Behind each faint oval catalogued lies countless hours of exposure, calibration, and debate. Teams argue over whether a smudge is real or artifact, whether its distance places it in a group or leaves it adrift. Conferences include sessions where astronomers present candidates and others challenge them, sharpening both claims and methods. The faintest galaxies demand the brightest scrutiny, and in this crucible, science matures. The silence of these galaxies is not only scientific, but poetic. To glimpse a faint smear and know it is 100,000 light-years wide, filled with stars older than civilizations, is to confront humility. They ask for patience, for trust in the faintest signals, and they reward that trust with revelations about extremes, halos that are almost all dark, or systems that are almost all stars, or galaxies that seem to contradict the very model used to explain them. Each silent galaxy is both an observation and a question mark written into the night. As you drift deeper into thought, imagine walking through a gallery of cosmic paintings. Bright spirals draw the eye first. Then, slowly, you notice the backgrounds, the pale shapes, the hints of form that almost vanish into blackness. These are the silent galaxies. Their brushstrokes are lighter, their palettes muted, but without them, the canvas of the universe would be incomplete. In the next part of our journey, we will consider what these quiet systems teach us about dark matter itself. If halos can host massive galaxies with almost no stars, or faint galaxies with almost no halos, then the very scaffolding of the cosmos may be more complex than we thought. Silence, in this sense, is not an absence, but a clue. Dark matter has long been the invisible scaffolding of the cosmos. Without it, galaxies as we know them would not exist. Stars alone do not generate enough gravity to bind a spiral disk or stabilize the motions of clusters. The unseen mass must be there, wrapping galaxies in halos that extend far beyond visible edges. The cosmic web itself, those filaments we map across billions of light years, only forms because dark matter collected first, pulling luminous matter into its embrace. For decades, this model has been the backbone of cosmology. Then the silent galaxies appeared, and the backbone seemed less simple. At first glance, the faintest galaxies were expected to reinforce the case for dark matter. If light is sparse but galaxies endure, then something unseen must be holding them together. And indeed, many ultra-diffuse systems displayed evidence of massive halos, confirmed by globular cluster counts and velocity dispersions. Dragonfly 44 became the emblem of this scenario, a pale wisp of light orbiting in the Coma cluster, but with mass estimates comparable to the Milky Way. Its faintness only highlighted the grip of its dark halo. Such cases seemed to prove dark matter's dominance even more forcefully. But then came contradictions. Some ultra-diffuse galaxies, like DF2 and DF4, appeared to move without dark matter's invisible hand. Their stars drifted at speeds too low to require massive halos. Their globular clusters orbited sedately, as if no hidden mass lurked. If those measurements held true, they represented galaxies without dark matter. The implications were profound. Dark matter had been assumed to be the universal skeleton on which galaxies hang. To find one, or more, that lacked, it was like discovering bones made of glass, or a body that stands without a skeleton at all. The debate intensified. Could DF2 and DF4 be illusions, their distances mismeasured? New observations sought to clarify. Deeper exposures with the Hubble Space Telescope refined the brightness of red giants, confirming the galaxy's placement near NGC 1052. Radial velocity measurements were repeated with improved instruments. The results still pointed to an absence, or at least a radical deficiency, of dark matter. One galaxy could have been an anomaly. Two in the same group suggested a new category. Explanations multiplied. Some proposed tidal stripping, that these galaxies were once ordinary, but gravitational encounters with a larger neighbor peeled away their halos, leaving only faint stellar remnants. Others argued for alternative theories of gravity, suggesting that the apparent need for dark matter in most galaxies might be a misunderstanding of how gravity behaves at low accelerations. If some galaxies could mimic dark matter-free states, then perhaps the deeper laws of motion deserved another look. Still, counterexamples like Dragonfly 44 reminded everyone that dark matter cannot be discarded so easily. Ultra-diffuse galaxies with massive halos and ultra-diffuse galaxies with none pointed to diversity, not uniformity. Dark matter was not behaving like a simple, universal ingredient. It seemed to allow exceptions, outliers, contradictions. That very messiness made the silent galaxies powerful test cases. They illuminated the edges of theory, the places where models fray. Consider the broader stakes. Dark matter has not been detected directly in laboratories. Its existence rests on inference from cosmic motions, gravitational lensing, and structure formation. For decades, the consistency of those inferences across scales provided confidence. But the faint galaxies show that the relationship between stars and dark matter is not one-to-one. Sometimes halos grow stars. Sometimes halos remain barren. Sometimes stars manage to exist without halos at all. The cosmos, it seems, is willing to play multiple games with the same pieces. These contradictions feed into debates about the nature of dark matter itself. If it is cold and collisionless, as most models assume, then halos should always cradle galaxies. If it is warm, fuzzy, or self-interacting, then the behavior could be subtler, creating a spectrum of outcomes. Silent galaxies become laboratories for these possibilities. By counting how many lack halos, by measuring how many have unexpectedly rich globular cluster populations, we can constrain what dark matter is allowed to be. The tension also sharpens the question of environment. If halo stripping explains dark matter-deficient galaxies, then such systems should cluster near larger galaxies or dense regions. If they exist in isolation, then stripping cannot be the whole story. Each new discovery pushes models to account for both context and content. In this way, the silent galaxies become cosmic auditors, checking our theoretical bookkeeping for errors. Behind all the technical detail lies a deeper truth. The quietest galaxies speak loudly about what we do not understand. Their very existence tells us that the scaffolding of the cosmos is not a uniform grid, but a tapestry of exceptions. To study them is to accept humility, that the grandest models, elegant in equations and simulations, may stumble in the face of a smudge barely visible on the sky, and in that humility lies opportunity. The silent galaxies are not roadblocks, but gateways. By examining them, astronomers sharpen not only their instruments, but also their imagination. Each faint smear, each ghostly oval, is a chance to discover whether dark matter is exactly what we think it is, or whether the universe is whispering about something stranger still. As we move forward, we will look at how these contradictions ripple into cosmology as a whole. If dark matter behaves unpredictably at the scale of galaxies, then what does that mean for the structure of the universe at large? Could the cosmic web itself carry silent strands we have not fully recognized? Could the distribution of voids and filaments bear the fingerprints of galaxies that do not play by the usual rules? These are the questions that await us in the chapters ahead. When astronomers speak about the cosmic web, they describe the largest pattern ever observed. A network of filaments and nodes stretching across billions of light years. Galaxies cluster where the strands intersect, like pearls threaded on invisible strings. Between these intersections lie immense voids, regions so sparse that they challenge the imagination. The web is the architecture of the universe, and it is drawn by gravity's hand acting upon dark matter. To place any galaxy within this web is to ask not only where it lives, but also how its environment shapes its nature. The silent galaxies, faint and fragile, occupy roles in this grand structure that are as revealing as they are enigmatic. Traditionally, maps of the cosmic web are built using bright galaxies and clusters. These luminous markers trace filaments like streetlights along a road. The assumption has been that wherever there is mass, there are bright galaxies to reveal it. The silent galaxies complicate this picture. Their faintness means that traditional surveys often miss them, especially at greater distances. As newer instruments probe deeper and wider, astronomers are finding that the web is more populated than once thought. The quiet galaxies, overlooked before, contribute a chorus of whispers that fills out the symphony. What is striking is how these galaxies distribute themselves. In clusters, they are plentiful, spread across the outskirts, like satellites orbiting a city. Their abundance suggests that cluster environments are fertile grounds for creating or preserving diffuse systems. Processes like ram pressure stripping, tidal harassment, and early quenching may all play roles. But faint systems are not confined to clusters alone. Surveys reveal that some float in the filaments themselves, marking strands of the web that were previously invisible. These discoveries imply that the web is not only a skeleton of bright lights, but also a fabric woven with softer threads. Understanding this distribution is vital. If faint galaxies are more common in filaments than in voids, it strengthens the picture of hierarchical growth, small halos forming along strands, merging into larger systems at intersections. If, however, some are found adrift in voids, far from the main highways of structure, then we must ask how they survived in such emptiness. Were they thrown there by gravitational slingshots, or did they form quietly in the margins, far from the drama of cluster assembly? Each discovery rewrites the fine print of our cosmic census. Large-scale surveys are now paying attention to these questions. Instruments like the Vera Rubin Observatory will scan the entire southern sky repeatedly, allowing astronomers to build time domain maps of diffuse systems. Euclid and Roman will add lensing data, tracing how dark matter filaments bend light from background galaxies. By combining these efforts, scientists hope to place the silent galaxies precisely within the web, not as statistical afterthoughts, but as integral actors. The result will be a richer, more inclusive map, one that acknowledges the quiet majority alongside the bright elite. The implications stretch beyond demographics. Cosmological simulations must reproduce not only the bright galaxies we see, but also the dim ones we are beginning to count. If simulations fail to create enough ultra-diffuse systems, or if they place them in the wrong environments, then something in the physics is incomplete. It could be feedback, it could be the nature of dark matter, or it could be the influence of cosmic reionization. Silent galaxies are not side notes. They are test cases for the fidelity of our entire model of structure formation. Philosophically, their place in the web teaches us humility. The grandeur of the cosmic map is not only in its glowing filaments, but also in its shadows. A web traced only by the brightest galaxies is like a city map that shows only skyscrapers, ignoring houses, gardens, and alleys. The silent galaxies are those alleys, subtle, often hidden, but essential to the full character of the cosmos. Without them, our map is incomplete, our sense of structure skewed towards spectacle. To visualize this, imagine standing above a great city at night. From afar, you see the brightest towers, the lights that declare themselves loudly. But as your eyes adjust, smaller glimmers appear. Streets, neighborhoods, quiet corners that make the city livable. The cosmic web works the same way. First, we saw the towers. Now, with patience, we begin to glimpse the neighborhoods, the faint ovals that tell us the universe is richer, more varied, more lived in than we once assumed. As we move deeper into this story, the question grows sharper. If the silent galaxies fill the web, what do they tell us about the cosmic balance between light and mass? Are they evidence that dark matter sometimes collects without sparking abundant star formation? Do they show us the limits of baryonic physics in a universe dominated by the unseen? Or do they hint at subtler processes we have not yet imagined? These are the mysteries that echo in their silence. In the next part of our journey, we will focus on how these galaxies connect to the cosmic voids themselves, the vast dark expanses where silence is not confined to a single system, but reigns across hundreds of millions of light years. If galaxies whisper, then voids are the pauses between sentences, and to understand them is to learn the rhythm of the universe. In the grand tapestry of the universe, voids are the darkest threads. They are not places of nothingness, but they come close. Immense expanses where matter is scarce, where galaxies are few, and where silence reigns on scales far greater than any individual system. To speak of a void is to speak of distance measured in hundreds of millions of light years, a volume so vast that whole superclusters could drift within its borders. And within these deserts of creation, the presence or absence of silent galaxies becomes a key to understanding how the cosmos balances fullness and emptiness. At first, astronomers thought voids were nearly empty. Early galaxy surveys revealed patterns of clustering, strings of bright galaxies tracing filaments, and then great gaps with almost nothing inside. The Bootes void, discovered in 1981, stunned researchers with its enormity. Nearly 330 million light-years across, containing only a handful of galaxies where thousands were expected. It seemed the universe contained vast caverns of silence, spaces between the glowing architecture of the cosmic web. But as instruments grew sharper and surveys grew deeper, the voids turned out to be not entirely barren. Dim dwarfs, faint smudges, and especially ultra-diffuse systems began to emerge inside them. They were rare, but they were there, holding fragile court in the silence. These galaxies carried profound significance. If bright galaxies avoid voids, then the faint ones become ambassadors of presence, showing how structure persists even at the edges of cosmic absence. Why would such systems form in voids at all? The answer lies partly in timing. The density of matter in a void is low, so the collapse of gas into halos is slow. Bright galaxies may fail to ignite because conditions are too thin to support abundant star formation. But smaller halos, with modest amounts of gas, can sometimes collect enough material to form faint galaxies. These become quiet survivors, too fragile to flourish in clusters, too small to compete with spirals, but stable in the empty calm of a void. Their silence is not imposed by stripping or harassment, but by the simple absence of neighbors. Studying void galaxies is challenging. By definition, they are far from the crowded skies of clusters, meaning fewer bright landmarks to measure distances against. Astronomers rely on redshift surveys to place them within the three-dimensional structure of the cosmos. Each faint dot is mapped not just in the sky, but in space, marking the contours of emptiness. Slowly, a richer picture emerges. Voids are not perfectly empty balloons, but lacework filled with faint whispers. The presence of silent galaxies redefines them, turning voids from absences into minimalist canvases. Void galaxies also test theories of cosmology. If dark matter is cold and collisionless, voids should contain small halos, even if they rarely grow large galaxies. If dark matter has different properties, if it is warm, fuzzy, or self-interacting, the number of halos in voids could change. Silent galaxies become the litmus test. Count them, measure them, and you can constrain what dark matter is allowed to be. They also test galaxy formation itself. If dwarfs exist in voids, then star formation can proceed under the leanest conditions imaginable. That resilience speaks volumes about the adaptability of cosmic processes. The silence of voids is more than scientific. It is also philosophical. To imagine a galaxy alone in such emptiness is to confront the fragility of existence. Imagine standing on a planet within one of these galaxies, looking up at a night sky. Instead of a Milky Way arcing bright across the heavens, you might see only a thin scattering of stars. The cosmic neighbors that comfort us here would be absent. The universe would feel not like a bustling city, but like an endless plain. In such a place, silence is not just an observational category, it is a lived experience. Astronomers sometimes describe voids as cosmic laboratories. They are free of the messy interactions that dominate clusters. No tidal stripping, no ram pressure winds, no violent mergers. Galaxies in voids evolve in comparative isolation, their histories written with minimal disturbance. By studying them, we glimpse the baseline behavior of galaxy formation, the story told when the universe is left to its own devices. In this sense, voids are not just absences, but control experiments on a cosmic scale. What has emerged from these studies is a paradox. Voids are both silent and eloquent. Silent because they lack the bright galaxies that catch the eye. Eloquent because the galaxies that do exist inside them are profound teachers. They show us resilience, minimalism, and the fine balance between light and darkness. They remind us that creation does not only thrive in abundance, but also persists in scarcity. As we leave this chapter, hold in your mind the image of a lone faint galaxy drifting in the heart of a void. Around it lies darkness on scales almost unimaginable, but within it burn stars as real as the ones above our own heads. Their light travels across emptiness, patient and unhurried, carrying the same message as all the cosmos. Silence does not mean absence. It means we must learn to listen more carefully. In the next part of our journey, we will turn from voids to time. The silent galaxies are not only scattered across space, but also across history. By studying their stars, astronomers reconstruct their pasts, when they formed, when they faltered, and how long they have whispered across the cosmic night. Every galaxy carries a memory. Its stars are not only points of light, but records of the conditions in which they were born. Their colors, compositions, and motions tell stories that no written chronicle could capture. For bright spirals and giant ellipticals, those stories are loud and layered, filled with multiple generations of stellar birth and death. For the silent galaxies, the record is different. It is quieter, simpler, sometimes truncated, but precisely in that silence lies its value. These galaxies are fossils of the universe, archives of ancient history written in faint starlight. When astronomers look into an ultra-diffuse galaxy, they often see populations dominated by old stars. Red giants glow faintly, their atmospheres enriched by elements forged in earlier epochs. The absence of young blue stars tells us that star formation ended long ago, perhaps billions of years in the past. The very lack of variety is instructive. It shows that these galaxies used their fuel early, or lost it before later generations could form. Their silence in the present is the echo of ancient voices. Spectroscopy sharpens this narrative. Even in faint systems, careful observations of integrated light reveal absorption lines corresponding to specific elements. Magnesium, calcium, iron, carbon, each leaves its mark. The relative abundance of these elements compared to hydrogen and helium becomes a code. If a galaxy is rich in alpha elements like magnesium and oxygen, it means its stars formed quickly, in a burst of activity dominated by massive stars that exploded as core collapse supernova. If iron dominates, it signals that slower type Ia, supernovae, had time to contribute, spreading heavier elements over longer spans. Silent galaxies with their low metallicities and alpha-enhanced signatures often show evidence of rapid early formation followed by long dormancy. Color magnitude diagrams, painstakingly built by resolving individual stars with the Hubble space telescope or the James Webb, deepen the picture. Each dot on such a diagram corresponds to a star's brightness and color. Together, they form sequences that trace stellar lifetimes. For faint galaxies, the diagrams often show well-defined red, giant branches, horizontal branches, and main sequences truncated at low masses. The scarcity of bright blue stars confirms their quiescence. In some cases, subtle features hint at a brief second episode of star formation, perhaps triggered by a passing stream of gas. But the dominant message is still quiet longevity. Most of the stars are ancient. This makes silent galaxies time capsules. They preserve what the universe was like in its early epochs, when ionization had only just cleared the cosmic fog, and small halos fought to keep their gas. Their stars record the chemical enrichment of that era, the balance between early bursts and later quenching. They provide a check on simulations of galaxy formation. Does theory predict the same star formation histories, the same metallicities, the same quiet endpoints? If not, then theory must adapt. Globular clusters add another dimension. These dense knots of stars are themselves ancient, often older than 10 billion years. A faint galaxy with an unexpectedly large population of globulars becomes doubly valuable. The clusters act as both mass tracers and historical witnesses. Their ages, metallicities, and dynamics can reveal whether the host formed in a single rapid collapse or through mergers of smaller fragments. In some silent galaxies, the globular clusters appear almost extravagant, outshining the main body in importance. They suggest that even when star formation faltered overall, some regions condensed into enduring brilliance. Stellar archaeology in these galaxies is not easy. Long exposures are required, and the faintness of individual stars pushes instruments to their limits. For nearby diffuse systems, like those in the Virgo cluster or orbiting Andromeda, detailed star counts are possible. For more distant ones, astronomers must rely on integrated light, stacking observations to pull out subtle features. Each success feels like unearthing a relic, a shard of pottery from a forgotten civilization. The stars themselves are the artifacts, glowing softly across the void. What emerges from this research is a vision of resilience. The silent galaxies may not shine brightly, but they endure. Their stars have survived billions of years, weathering cosmic reionization, cluster tides, and the stripping of gas. They are survivors not by strength, but by persistence. Their silence is not failure, it is testimony. They remind us that the universe values variety, that not all galaxies must be spirals or giants. Some exist simply to preserve memory. There is also a poetic resonance here. Imagine standing in one of these galaxies, beneath a sky of faint red stars, with few bright companions. The night would be subdued, less dramatic than ours, but every star above you would be ancient, each one older than recorded human history. To live there would be to inhabit a fossil, a home built entirely from the remnants of the early universe. It would be quieter, dimmer, but also profound, like living inside a museum where the exhibits are alive and glowing. As we carry this thought, we prepare to follow the next thread of the story. What these stellar populations tell us not only about the past, but also about the future. Silent galaxies remind us that cosmic history is not linear. It pauses, it falters, it whispers. In the next part, we will consider how their survival informs our predictions for the destiny of galaxies across time, and what silence might mean for the universe itself. Galaxies, like living beings, carry life cycles. They are born from collapsing gas clouds, grow by accreting material, mature through star formation and mergers, and eventually decline when their fuel is exhausted. For spirals like our Milky Way, this process is dramatic. Spirals wind tighter, star formation ebbs, and the system slowly transforms into something quieter. For giant ellipticals, the story is one of rapid growth and long quiescence. But silent galaxies, those faint and diffuse, offer a different kind of future vision. Their very persistence hints at how the universe itself may age, dimly, quietly, with whispers rather than fireworks. Consider first the fate of their stars. Most of the stars in silent galaxies are already old. Red giants dominate with low mass, main sequence stars quietly burning hydrogen at a slow pace. These smaller stars are patient. They will endure for tens or even hundreds of billions of years, long after the brighter, heavier stars in other galaxies have died. In this sense, silent galaxies are previews of the universe's twilight, a time when only small, dim stars remain, each giving off just enough light to hold back the dark. Their dynamics also speak to endurance. Ultra-diffuse galaxies that retain dark matter halos appear remarkably stable. Even with little starlight, their structures persist, orbiting within clusters or floating along filaments. They resist disruption, not by brightness, but by gravity's invisible hand. In a universe that will one day expand into near emptiness, such systems suggest that faint, dark matter-bound galaxies could remain as survivors, drifting in silence across unimaginable epochs. But what about those that appear to lack dark matter? Their futures may be more fragile. Without deep halos to hold them together, their stars may disperse over time, blending into the intracluster light, the faint glow that fills the spaces between brighter galaxies. In that case, their silence is temporary. They are whispers that eventually fade entirely. Their memory preserved only in the streams of stars stretched across the sky of a cluster. If so, they remind us that even silence can be fleeting. The broader lesson is that cosmic destiny is not singular. Different galaxies will age differently. Bright spirals will burn through their gas, transform into quiescent systems, and merge into larger forms. Giant ellipticals will continue to glow faintly with old stars, and the silent galaxies will persist as fossils or dissolve into diffuse light, depending on their halos. The future of the cosmos will be a patchwork of outcomes stitched together by the threads of dark energy and expansion. Silent galaxies also speak to the role of dark energy in the ultimate fate of the universe. As expansion accelerates, galaxies will drift farther apart until even the nearest neighbors recede beyond reach. In that far future, local groups will become isolated islands. Within each island, silent galaxies may remain as dim companions to brighter ones, or as remnants adrift in the void. Their low luminosity will make them hard to notice, but they will still carry mass, still orbit, still whisper across cosmic time. They are reminders that endurance is not always visible. Philosophers of science sometimes use these galaxies as metaphors for resilience. They are not triumphant, not spectacular, but they last. They persist in conditions that erase louder systems. They continue to exist, even when stripped, dimmed, and overlooked. In a universe whose future is governed by increasing emptiness, such persistence may be the truest lesson of all. Survival does not always mean thriving. Sometimes it means simply remaining, holding form against the erosion of time. If you imagine the far future of the cosmos, you might picture it as an immense, dim stage. Bright galaxies have merged, their fireworks of star formation long past. Supermassive black holes anchor the centers, glowing faintly as they consume the last trickles of gas. Across this dim backdrop drift the silent galaxies, faint ovals with sparse stars, patient companions to the cosmic dusk. Their role is not to illuminate, but to remind that the universe is not ending abruptly, but fading gently, carrying its history into silence. Astronomers call this vision the degenerate era, a time when star formation ceases, when only the smallest stars remain, and when galaxies become shadows of their former selves. Silent galaxies are previews of that era. They show us how a system can look when growth is over, but survival continues. To study them is to time travel forward, to glimpse the dusk that awaits all galaxies eventually. There is comfort in this vision. It tells us that silence is not loss, but transformation. The universe is not dying, but aging, moving from its brilliant youth to a quieter maturity. Silent galaxies are the elders of this cosmic family, teaching us what patience looks like on scales far beyond human life. They assure us that even as brightness fades, existence continues. As we move into the next stage of this story, we will shift from the future back to the present, asking what these galaxies teach us about our own Milky Way. For they are not distant, curiosities alone. They are also mirrors. By studying them, we can glimpse what parts of our galaxy's destiny may already be written, and what choices of environment and history shape a galaxy's fate. The Milky Way feels immense to us. From our vantage point on Earth, its disk spans the sky like a luminous river, billions of stars forming a single ribbon across the dark. Its spiral arms are alive with nebulae and clusters, and its core hides a supermassive black hole with a mass of 4 million suns. To most observers, the Milky Way is the archetype of a galaxy, grand, structured, and filled with brilliance. But when we compare it to the silent galaxies scattered across the cosmos, we begin to see our home in a different light. The contrast reveals what is ordinary and what is extraordinary about our place in the universe. For one, the Milky Way is rich in gas. This reservoir allows it to continue forming stars at a steady pace, adding new blue giants and clusters every few million years. Silent galaxies, by contrast, are usually starved of gas. Their light is dominated by older populations, and their silence reflects an inability to replenish fuel. The difference tells us that our galaxy has been fortunate. Its environment, its dark matter halo, and its cosmic history have all conspired to keep it alive. The Milky Way is not immortal, but compared to its silent cousins, it is thriving. Surrounding the Milky Way are its satellites, dwarf galaxies that orbit like companions around a parent. The large and small Magellanic Clouds are visible even to the naked eye from southern latitudes, their irregular forms bright and full of gas. But most of our satellites are fainter, dim smudges only detected in careful surveys. Some of these satellites resemble the silent galaxies beyond reach, diffuse, gas-poor, and dominated by old stars. The Sagittarius dwarf, for example, is in the process of being shredded by the Milky Way's gravity, its stars stretched into tidal streams. Other satellites have barely enough light to register, yet they are bound to us, surviving quietly in our halo. The study of these faint companions has exploded in the past 2 decades. Wide-field surveys like the Sloan Digital Sky Survey and the Dark Energy Survey have revealed dozens of ultra-faint dwarfs orbiting the Milky Way. Each one is a laboratory for dark matter, chemical evolution, and star formation under extreme scarcity. They show us that our galaxy's halo is not empty, but littered with silent voices. These local examples are more than curiosities. They are the closest cousins of the silent galaxies we see in distant clusters, and they allow us to study silence in detail. Chemical analyses of stars in these dwarfs reveal staggering antiquity. Some stars contain fewer heavy elements than almost any others known, indicating they were born from gas enriched by only 1 or 2 supernovae. They are fossils from the dawn of star formation, preserved in galaxies so faint they were almost invisible. By examining them, astronomers reconstruct conditions from 13 billion years ago, when the Milky Way itself was young. In this way, silent galaxies orbiting our own become windows into the first chapters of cosmic history. The dynamics of these satellites also illuminate the dark matter halo of the Milky Way. Their orbits, their velocities, and their dispersions reveal the depth and shape of the halo we cannot see. Some appear to be dominated by dark matter, with mass-to-light ratios of hundreds or even thousands. Others are so diffuse that they test the limits of gravitational binding. By mapping them, we not only understand their silence, but also the skeleton of our own galaxy. Silent companions act as tracers, sketching the boundaries of our cosmic home. Philosophically, these comparisons remind us that the Milky Way is not typical. To us, it feels ordinary because it is familiar. But in the grand census of galaxies, its brightness and star formation make it more privileged than most. Silent galaxies are the norm, not the exception. They vastly outnumber systems like ours, quietly filling halos and filaments with muted light. The cosmos is not built primarily from spectacular spirals. It is built from faint ovals that whisper. In knowing this, we see our home differently, not as a standard model, but as a fortunate outlier. There is also a lesson in humility. The fate of our satellites foreshadows our own. Just as the Sagittarius dwarf is being shredded, the Milky Way itself will one day be altered when it merges with Andromeda. Streams of stars will arc across the sky, and gas will be consumed. Over billions of years, our bright spiral will fade, perhaps leaving behind remnants that resemble the silent galaxies we study now. Silence, in this sense, is not distant. It is our destiny too. Imagine looking up from a planet within one of these faint satellites. The Milky Way would loom as a vast, glowing neighbor, dominating the sky. Your own galaxy would be a pale handful of stars, fragile compared to the giant next door. From that perspective, our home is not ordinary, but overwhelming, a cosmic metropolis overshadowing a village, and yet both are galaxies. Both hold stars and stories. Both contribute to the grand structure of the cosmos. As we carry this image, we prepare to move outward again. Silent galaxies around the Milky Way teach us about local silence, about fossils, preserved within our own halo. But the universe is not confined to our neighborhood. In the next part, we will explore how silence operates across clusters and groups, where the interplay of environment and gravity sculpts faint systems into diverse forms. There, silence becomes not just an individual trait, but a collective phenomenon, shaping the dynamics of whole regions of the cosmos. Clusters of galaxies are among the largest structures bound together by gravity. They are cities of the cosmos, filled with hundreds or even thousands of members, orbiting within a common halo of dark matter and suffused by hot gas that glows in X-rays. To study a cluster is to study density, interaction, and community. Every galaxy inside feels the presence of its neighbors through gravity, radiation, and the medium that fills the space between. It is here, in these crowded environments, that silent galaxies reveal some of their most striking traits. Their faintness is not only an intrinsic quality, it is also shaped, sometimes forced, by the places they live. In the outskirts of clusters, where the gravitational pull is weaker and the density lower, galaxies often retain some individuality. Spirals enter these regions with their disks still intact, their gas reservoirs still feeding star formation. As they move inward, the environment begins to change them. The hot intracluster medium, moving relative to the galaxies, acts like a wind. It strips gas from their disks in a process called ram pressure stripping. The denser the cluster, the stronger the effect. Over time, once bright galaxies lose their gas, star formation ceases, and what remains drifts towards silence. Other processes add to this transformation. Encounters between galaxies, called harassment, shake stars from their orbits and heat stellar disks. Repeated interactions over billions of years can puff up galaxies, diluting their light and turning them into diffuse systems. Tidal forces near massive ellipticals or the cluster core can stretch companions into elongated arcs, eventually leaving behind faint remnants that resemble ultra-diffuse galaxies. In these ways, clusters become factories of silence, mass-producing faint galaxies through environmental pressures. Observations of clusters like Coma and Virgo confirm this. They are littered with ultra-diffuse galaxies, far more than expected by chance. Some are round and smooth, relics of long-ago transformations. Others show subtle elongations, traces of ongoing harassment. Many lack gas, consistent with ram pressure, stripping. Their very abundance suggests that clusters are breeding grounds for silence, sculpting galaxies into faint shadows of themselves. But clusters also host extremes. Among the silent members, a few stand out for their mass. Dragonfly 44. In Coma, with a halo as massive as the Milky Way, but only a fraction of its stars, is one such case. It is a reminder that not all silence is weakness. Some silent galaxies hide strength beneath their faint exteriors, cloaked in darkness but resilient against disruption. Clusters, with their variety of conditions, allow both fragile remnants and dark giants to coexist. The intracluster medium itself becomes a stage for these processes. As galaxies lose gas, the stripped material enriches the cluster with metals and fuels faint intracluster light. This diffuse glow, barely perceptible, is the combined remnant of countless galaxies pulled apart. Silent galaxies both contribute to and are created by this process. They are both victims and authors of the diffuse light that suffuses clusters. Simulations show that the history of a cluster is written partly in its silent members. By counting how many ultra-diffuse galaxies exist in a cluster and comparing that number to its mass and age, astronomers can infer how long galaxies have been falling in, how often harassment occurs, and how strong the intracluster medium is. Silent galaxies become statistics, but each one also remains a story, a smudge that tells us about survival and transformation under pressure. There is also a broader philosophical resonance. In a cluster, brightness dominates the eye. Giant ellipticals glow at the center. Spirals twist in arcs of starlight. But the silent galaxies, though faint, outnumber the giants. They are the unlit apartments of the cosmic city, the quiet neighborhoods that make up most of the population. Without them, the city would not be complete. Their silence is not emptiness but balance, reminding us that abundance and faintness are both parts of community. Imagine drifting through a cluster, past glowing giants and sharp spirals, until your eyes adjust to the dim shapes all around. They are everywhere. The faint ovals, the diffuse smudges, the galaxies with light stretched thin. They do not announce themselves, but they fill the space. In their collective silence, they define the character of the cluster as much as the bright members do. Their quiet endurance is the chorus beneath the symphony. In the next part of our journey, we will turn from clusters to groups, the smaller gatherings of galaxies that more closely resemble our local group. There too, silence plays a role, shaping companions and preserving fossils. By comparing clusters, groups, and isolated systems, we will see how environment sculpts galaxies differently and how silence adapts to context across the universe. Clusters, with their thousands of galaxies, are cosmic metropolises. But most galaxies do not live in such bustling environments. Instead, they reside in smaller communities, galaxy groups. Groups contain a handful to a few dozen members, bound together by gravity, sharing a common dark matter halo. Our own Milky Way, along with Andromeda and their satellites, is part of one such group, the local group. These quieter environments provide a different stage for silent galaxies, one where their histories are written less by violence and more by gentle shaping. Groups are crucial because they represent the most typical environment in the universe. While clusters are spectacular, they are rare. Groups, on the other hand, are abundant. If you were to place yourself randomly in the cosmos, odds are you would land in a group, not a cluster. That means understanding silence in groups is central to understanding silence in general. In groups, galaxies are close enough to interact, but not so crowded that encounters are constant. Tides occur, but more slowly. Ram pressure stripping is weaker, since the intragroup medium is not as dense as that in clusters. As a result, the processes that create silent galaxies here tend to be subtler. Gas can still be removed, but gradually. Star formation can still quench, but over longer timescales. Harassment is less common, but mergers between dwarfs may still occur. Silence in groups often comes not from abrupt shocks, but from quiet starvation. The local group illustrates this well. The Milky Way and Andromeda dominate, with Triangulum as a smaller spiral companion. Around them swarm dozens of dwarfs, most of them faint and gas-poor. Many of these dwarfs are silent galaxies, their star formation long-ended. Some, like the Sculptor and Fornax dwarfs, contain stars that tell of early bursts, followed by billions of years of quiescence. Others, like the ultra-faint dwarfs discovered by recent surveys, are little more than glimmers, bound by halos but starved of light. Why are they silent? Some fell into the halos of the Milky Way or Andromeda long ago, where tidal forces and gentle stripping removed their gas. Others formed stars early, then lost their fuel during reionization. Their silence is partly environmental, partly ancestral. The diversity is striking. Even within one group, galaxies follow multiple pathways to faintness. The dynamics of groups make them fertile ground for comparison. If clusters mass-produce silence through harsh conditions, groups create it with nuance. That makes them valuable laboratories. By studying the faint dwarfs in groups, astronomers test theories of quenching, feedback, and dark matter under intermediate conditions. They also provide analogues for what happens in other groups across the universe. Observations have shown that groups often contain extended networks of tidal streams. These are the remnants of dwarfs pulled apart by larger members. The Sagittarius stream around the Milky Way is one example, stretching across the sky as a ribbon of stars. In Andromeda, similar streams trace the fates of past companions. Silent galaxies contribute to this architecture, their stars redistributed into halos and intragroup light. Their voices are not gone. They are spread out, blended into the background. Chorus. Some groups also host ultra-diffuse galaxies. Though more common in clusters, they are not absent from smaller communities. Their presence in groups raises questions. Were they formed there, or did they arrive as interlopers, stripped from clusters and captured later? Each case is a test of how galaxies move between environments, carrying their silence with them. The local group also teaches us about survival. While some dwarfs have been disrupted, others endure, orbiting for billions of years with their faint stars intact. These survivors remind us that silence is not always fragility. It can be persistence, a form of resilience in the face of stronger neighbors. They whisper across time, holding on where brighter systems evolve dramatically. From a philosophical perspective, groups are mirrors of human communities. There are giants, like the Milky Way and Andromeda, but also quiet villages of stars, often overlooked. The giants dominate the skyline, but the villages hold memory and character. To study the group as a whole is to appreciate both scales, the towering and the humble, the loud and the silent. Together, they form the ecosystem of the cosmos. Imagine drifting beyond our Milky Way, across the void that separates us from Andromeda. Around you would float faint companions, dim dwarfs barely visible, their stars ancient and red. Some would be dissolving into streams, their identities fading. Others would remain intact, orbiting patiently. Beyond them lies Triangulum, small but bright, and then the emptiness that leads outward. It is a quiet neighborhood, vast by human standards but modest compared to clusters. And within it, silence is everywhere, subtle, enduring, profound. As we move forward, we will widen the lens once more. Groups show us silence in modest environments, clusters in crowded ones. But silence also manifests in isolation, galaxies that live entirely alone, far from any neighbor. In the next part, we will turn to those solitary wanderers to see how silence evolves when the only companion is the void itself. Not all galaxies live in the company of neighbors. Some reside in clusters, surrounded by thousands. Others share modest groups, like our own local group. But there exists another category, galaxies that live alone, in isolation, far from clusters and groups. For these solitary wanderers, silence takes on a different meaning. It is not imposed by violence or shaped by interaction. It is the product of solitude, the natural rhythm of a galaxy evolving without companionship. Silent galaxies in such environments reveal what happens when a system is left entirely to itself, whispering across time in cosmic solitude. Isolation in astronomy is not simply being far away. It is being far enough that gravitational influences from other large galaxies are negligible. An isolated galaxy may travel through a filament, but no giants loom nearby. Its nearest neighbor may be millions of light-years distant, too far to tug, strip, or harass. In such conditions, a galaxy becomes an experiment in nature's default behavior. What unfolds when no one interferes? Silent galaxies in these settings often tell stories of starvation. Without fresh gas inflows from mergers or companions, they slowly exhaust their fuel. Star formation falters, leaving behind ancient populations of red and yellow stars. Their diffuse structures reflect not harassment, but stasis, low density, systems that never gathered enough mass to ignite brightly in the first place. They are cosmic minimalists, existing quietly without drama. But isolation does not always mean fragility. Some isolated ultra-diffuse galaxies appear remarkably stable. Bound by dark matter halos, they endure for billions of years, slowly orbiting through filaments like quiet drifters. Others reveal surprising richness in globular clusters, as if compensating for their lack of bright stars with dense knots of ancient light. Each case adds nuance to the idea of silence. It can be frailty, but it can also be strength hidden behind a faint exterior. Studying isolated galaxies is difficult because they are rare and faint. Clusters are easy to find. They are bright and concentrated. Groups are common. But isolated galaxies hide in the margins. They require wide surveys to detect and careful confirmation to ensure they are truly alone. Their discovery is always a triumph of patience, like finding a single candle flame in a desert at night. Once confirmed, they become crucial laboratories. By comparing them to cluster or group counterparts, astronomers can disentangle which aspects of silence come from environment and which come from intrinsic processes. One striking result is that isolated silent galaxies often retain more gas than their clustered cousins. Without ram pressure stripping or tidal harassment, they are not robbed of fuel as quickly. But their star formation is still inefficient, spread thin across their diffuse structures. They are like households with a pantry always stocked, but rarely cooked from. Resources exist, but the activity is minimal. The reasons are complex. Low surface densities, weak gravitational potentials, and fragile disks all conspire to keep their light low. Silence persists even without predators. Philosophically, these solitary systems embody cosmic loneliness. Imagine living on a planet inside such a galaxy. The night sky would lack the brilliance of bright companions. No Andromeda glowing nearby, no crowded cluster filling telescopes with hundreds of galaxies. Instead, only faint stars and the distant glow of filaments would appear. The universe would feel vast and empty, your home a small island adrift in an endless ocean. For us, who find meaning in connection, such solitude feels haunting. For the galaxy, it is simply existence. In many ways, isolated silent galaxies serve as reminders of balance. They show us that not all silence is environmental. Some is inherent. They whisper that even in the absence of conflict, faintness can persist. The universe allows variety, and some galaxies are born to be quiet. Their role is not diminished by their solitude, it is amplified. By drifting alone, they reveal the boundaries of what galaxies can be. As we prepare to continue, hold in mind the image of one such galaxy, glowing faintly in emptiness, its stars ancient, its gas unused, its companions absent. Silence is not only around it but within it, woven into every corner. In the next chapter, we will step back and consider how silent galaxies across all environments, clusters, groups, voids, and isolation, combine into a larger picture. Together, they teach us not only about galaxies themselves, but also about the fundamental laws that guide the cosmos. As we journey through the universe, we have seen silence take many forms. In clusters, silence is sculpted by violence, ram pressure stripping, harassment, and tidal forces. In groups, it is shaped, more gently, by starvation and quiescence. In voids, it emerges from scarcity, the inability of halos to gather fuel. In isolation, silence is intrinsic, a natural outcome of galaxies left to evolve alone. Each environment provides a different melody in the cosmic symphony. When heard together, they reveal that silence is not an exception, but a theme, woven throughout the structure of the universe. The comparison begins with clusters. There, the abundance of ultra-diffuse galaxies is striking. Hundreds have been catalogued in places like Coma and Virgo, filling outskirts and cores alike. Their presence tells us that clusters are efficient factories of faintness. The density of galaxies, the hot intracluster medium, and the relentless gravity of central giants conspire to quiet smaller members. Silence here is forced, imposed from the outside. It is a testimony to the harshness of crowded environments, where only the most massive retain their voices, while the rest fade into whispers. Groups provide a contrast. In these smaller communities, silence arises from subtler processes. Gas is not stripped suddenly, but consumed gradually. Star formation does not stop abruptly, but wanes over billions of years. Dwarfs orbiting larger members lose fuel slowly, their silence emerging as a long dusk instead of a sudden night. The local group is a microcosm of this. Some companions disrupted, others still intact, all carrying fossils of their past. Silence in groups is more diverse, less predictable, reflecting the complex balance between nurture and nature. Voids push the theme further. Here, silence is not imposed by environment, but by emptiness itself. Faint galaxies survive in sparse conditions, forming stars inefficiently, carrying ancient populations across cosmic deserts. Their silence is profound because it is contextual. Surrounded by darkness, their faint light is amplified in significance. Each void galaxy becomes a beacon of persistence, a reminder that even in scarcity, creation endures. Silence here is not defeat, it is resilience. Isolation completes the picture. When galaxies evolve without neighbors, their silence becomes a kind of purity, No stripping, no harassment, no starvation by giants. Just inefficiency, fragility, or minimalism. Some thrive modestly, retaining gas but failing to ignite brightly. Others glow faintly with ancient stars, untouched for eons. Isolation shows us the baseline, what galaxies can become when left alone. Their silence is not forced, not contextual, it is inherent. When we compare these environments, patterns emerge. Silent galaxies are not confined to one type of setting. They exist everywhere. Their presence across all scales implies that faintness is not rare, but fundamental. The universe produces silence through multiple mechanisms, each reinforcing the other. It is as though the cosmos insists that not all galaxies should shout. Some must whisper, some must hum softly to balance the chorus. This universality makes them powerful tools for cosmology. By studying their abundance in clusters, we learn about environmental quenching. By analyzing them in groups, we test gradual processes of starvation. In voids, we constrain models of dark matter and structure formation. In isolation, we glimpse intrinsic limits of star formation efficiency. Together, they provide a comprehensive laboratory for testing the physics of galaxies. Silence, far from being marginal, is central to our understanding of the cosmos. Philosophically, the comparison reminds us that context shapes destiny. A galaxy in a cluster may be silenced by its neighbors. One in a void may be silenced by emptiness. One in isolation may be silenced by its own inefficiency. None of these outcomes is superior or inferior. They are simply varied responses to circumstance. The diversity of silence mirrors the diversity of life itself, where organisms thrive, adapt, or diminish depending on environment. In this sense, galaxies are not just physical systems. They are metaphors for resilience and fragility in equal measure. Imagine placing all these galaxies on a single canvas. Bright spirals and ellipticals dominate the center, glowing loudly. Around them, faint ovals cluster in silence, their voices subdued by environment. On the edges, small groups host dwarfs dimming slowly, while beyond lie voids with solitary beacons glowing faintly. At the far margins, isolated galaxies drift alone, whispers in the dark. The canvas becomes complete only when all voices are included. Without silence, the picture is distorted, skewed toward brightness, incomplete. In the next part of our journey, we will step from comparison into consequence. Silent galaxies do not only reflect their environments, they also affect them. By contributing stars to intracluster light, by enriching halos with metals, by tracing dark matter, they shape the ecosystems in which they live. Their silence is not passive, but participatory, altering the balance of their surroundings. Silence, in other words, has power. Up to this point, we have considered the silent galaxies as records, as fossils, as witnesses. Their faintness seemed to mark them as passive, as though they were simply the background against which brighter galaxies act out their dramas. But silence is not the same as passivity. Even the faintest galaxies exert influence. They add to the mass budget of the universe. They enrich their environments with stars and gas, and they serve as traces of the unseen structures in which they live. When viewed in this light, the silent galaxies shift from being observers to participants, quiet but essential actors in the unfolding story of cosmic evolution. One of the most striking ways they shape their environments is through intracluster light. When faint galaxies are stripped of stars by tidal forces or shredded entirely, their contents do not vanish. Instead, those stars drift into the cluster, spreading across hundreds of thousands of light years as a faint diffuse glow. This light is so dim that it is almost invisible, requiring deep exposures and careful subtraction to detect. But its existence is undeniable. It fills the spaces between galaxies with a ghostly sheen, a silent testimony to countless disrupted systems. Silent galaxies are among the primary donors to this intracluster reservoir. Their fading voices become part of a collective hum, adding to the shared light of the cluster community. This contribution is more than aesthetic. Intracluster light carries metals forged in stars, enriching the cluster medium. It alters the thermodynamic state of the hot gas that fills clusters, and it provides evidence for the frequency of tidal disruption. By measuring the brightness and distribution of this diffuse light, astronomers can estimate how many galaxies have been destroyed and when. Silent galaxies thus leave legacies that persist long after their individual forms dissolve. Their silence becomes permanent architecture woven into the cluster itself. Silent galaxies also shape their surroundings through chemical enrichment. Even small bursts of star formation generate supernovae, which fling heavy elements into space. In clusters and groups, these elements mingle with the intracluster medium, influencing cooling rates and the ability of future galaxies to form. Although each faint galaxy contributes only modestly, their sheer numbers make them significant. They are quiet, but they are many, and in aggregate they help to paint the chemical palette of the cosmos. The oxygen in a future star, the iron in a future planet, may trace back not to a luminous spiral, but to a faint whisper of a galaxy whose silence masked its importance. Another role lies in dark matter mapping. Because silent galaxies are faint, their dynamics are especially sensitive probes of the halos that host them. A bright spiral may conceal its dark matter distribution under layers of gas, star formation, and complex dynamics. A faint galaxy, with fewer moving parts, provides a cleaner test. By measuring the velocities of its stars or globular clusters, astronomers infer the depth of the surrounding halo. Some silent galaxies, like Dragonfly 44, confirm that dark halos can be immense, binding vast systems with little starlight. Others, like DF2 and DF4, raise puzzles by suggesting an absence of dark matter. In both cases, silent galaxies sharpen the contours of our models. Their faintness is not a weakness, but a magnifying glass, focusing attention on the invisible scaffolding of the universe. Silent galaxies also affect gravitational lensing. When a cluster lenses light from a background object, the distribution of mass, including faint galaxies, determines the lensing pattern. Ignoring silent members would lead to errors. Including them improves accuracy, making these galaxies silent architects of how we perceive distant light. Even their mass, dim as it may be, bends space-time, contributing to the cosmic geometry we observe. The accumulation of these effects underscores a truth. Galaxies do not need to be bright to matter. In fact, the faintest may influence their environments in ways disproportionate to their visibility. They enrich, they trace, they bend, they endure. They may not dominate the night sky as the Milky Way does for us, but they weave threads into the cosmic fabric all the same. Philosophically, this teaches us a lesson about quiet influence. Power is not always loud. Sometimes it is cumulative, subtle, distributed across many small actors instead of concentrated in a few giants. Silent galaxies remind us that history is written not only by the spectacular, but also by the humble. Their contributions are harder to see, but no less essential. Imagine standing at the edge of a massive cluster, looking inward. The bright galaxies catch your eye first, spirals, ellipticals, glowing in grandeur. But between them lies a faint glow, intracluster light spread like cosmic fog. That glow is made from silence, the remnants of countless faint galaxies. Without them, the cluster would be less massive, less enriched, less complete. Their silence is not absence, it is presence in a different form. As we prepare to move into the closing part of this journey, we will turn to synthesis. We have seen how silent galaxies live in clusters, groups, voids, and isolation. How they preserve history, shape environments, and hint at cosmic futures. In the final chapter, we will bring all these threads together, asking what silence ultimately means for our understanding of the universe and for the way we see our own place within it. We have walked a long path through the faintest corridors of the cosmos. From the outskirts of clusters to the emptiness of voids, From companions orbiting giants to solitary wanderers drifting alone, the silent galaxies have spoken in whispers. They have taught us that faintness is not absence but expression, not weakness but testimony. Their diffuse forms, their ancient stars, and their quiet endurance show us that the universe is more varied, more nuanced, and more humble than we often imagine. When we began, silence seemed like an anomaly, a puzzle to solve. Why would a galaxy be so faint, so diffuse, so fragile? But as we have seen, silence comes in many forms. In clusters, it is imposed by environment, harassment, stripping, and tides turning bright systems into pale remnants. In groups, it is gradual, gas consumed slowly, star formation waning with time. In voids, it is contextual, galaxies whispering against a background of emptiness. In isolation, it is intrinsic, faintness as the natural outcome of inefficiency and minimalism. Silence, then, is not a singular story, but a symphony of variations, each part reflecting a different facet of cosmic truth. The silent galaxies also remind us that brightness is not the only measure of importance. They contribute to intracluster light, enriching clusters with diffuse glow. They release metals into space, painting the universe with the ingredients for future stars and worlds. They map dark matter, exposing the scaffolding that bright galaxies conceal. Even in faintness, they shape the cosmos. They prove that quiet influence can be profound. In their stars, we find records of ancient times. Some hold fossils from the earliest epochs, low metallicity stars that preserve the memory of the universe's youth. Others contain swarms of globular clusters, dense knots that shine like jewels against the dim background. These records are gifts, time capsules that allow us to reconstruct the dawn of creation. Silent galaxies are not empty. They are archives, their silence filled with memory. As we imagine the far future, they give us previews of what is to come. Silent galaxies endure as dim survivors, holding form across billions of years, or dissolving into intracluster light that still enriches their environments. They are glimpses of the twilight of the universe, when brightness fades but existence continues. They whisper to us that the cosmos will not end in a sudden blaze, but in a long dusk, where the faintest stars still burn, patient and unhurried. And what of our own place in this? The Milky Way, bright and structured, feels eternal to us. But one day, it too will fade. Its gas will run out, its star formation will cease, and its spiral arms will dissolve into memory. Perhaps it will merge with Andromeda and become an elliptical giant. Perhaps it will leave behind remnants resembling the silent galaxies we study today. In that sense, silence is not distant. It is destiny. To look at faint galaxies across the sky is to glimpse our own future written in advance. Philosophically, silence carries lessons beyond astronomy. It teaches us that endurance does not always shout, that influence does not always blaze, that sometimes the most important contributions are quiet, cumulative, and humble. In a world and a universe, often captivated by spectacle, the silent galaxies remind us to listen for whispers. They remind us that completeness comes not from ignoring the faint, but from including every voice, however small. As we close this journey, imagine one last image, a vast cosmic canvas. Bright galaxies form the obvious strokes, spirals, and ellipticals, glowing like lanterns. But woven between them are faint ovals, silent galaxies barely visible. Together, they complete the painting. Without them, the canvas would be sparse, incomplete. With them, the universe is whole. If this calm journey into silence has given you peace, wonder, or a moment of reflection, I invite you to subscribe. Your presence, your quiet encouragement, is what keeps these stories alive. Each subscriber is a reminder that curiosity matters, that even in a noisy world, there is value in whispers. Thank you for listening, for caring, and for allowing silence to speak.